Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you, Satnan. Small crowd, so it shouldn't be a problem to, to hear each other. So, right on clue, yes. I organized a talk around the question that Satnan pretty much has asked. So, how can we argue that something has changed recently? Why should we look at this very old technology from a new point of view today? Can we actually use it? So I'll talk about the success story. And then some more controversial, forward-looking, whatever statements. Going forward, how far can we push this stuff? And what are the problems that we will likely face? So in two pictures, we all know what really has changed. Processors frequency was growing linearly anyways, and has been stuck as of 2005 roughly, whereas FPGA capacity has been growing exponentially according to the Moore law, right? And keeps on going. Now, this is not an apple to oranges comparison, because with processors, it is the frequency that we care for as a measure of performance. With a FPGA, it is the room that we have on it as a measure of performance, because we use spatial parallelism. The clock hasn't gone up that much in FPGA technology. And the disparity, however, is I should go over here, sorry about that. The disparity is still factor 8 or something. So that's the number one, the most obvious thing. But there are other things that are less obvious, perhaps. And that is not just processors, but all ASICs have the plateau for the clock.
It works switching the right clock, because I think it's not working.
It's not working?
We're trying to see how it works without it. Because it's distracting.
Better?
Let's give it a go for a couple of minutes.
Okay. So, here's a quick summary of the many things that happen in those that I the first two are basically the motivators for the so-called clock path. And here there will be no more exercise as new processes become more and more expensive, exponentially expensive. What is what there is just $4,000 million for the FPGA in the previous process, so $10 million.
Excuse me, sir. Use the microphone, yes. Yes, because it's on this side. Larsen, you stay. Yes, because
you have to record?
Yes. Thank you.
Sorry.
Put it a bit lower. Can you turn the feedback down?
Yeah, you lower the volume.
On this side, because
Can you just turn the feedback down? We don't just the speakers. Just
the volume. Can you lower the volume a little?
Yeah, it's possible, but
I'll shout and you lower the volume. Yeah, okay. Yeah, sorry about that. All right, so we are talking about new processes and how they affect ASICs, and projection that bigger and bigger FPGAs will be able to capture a bigger portion of ASIC runs, and companies will use FPGAs because they are good enough. They are going down in price. It's faster to develop anyways, and good enough is good enough. And the other consequence of the exponential growth is that the volume of ASICs that you have to sell in order to recoup your investment goes up exponentially. Now, the consideration of the GPU is one more of this philosophy. If you remember the RISC thing that the CPU does everything, is gone, it's done. It has had a profound effect, certainly on Microsoft, but on the industry at large. Now the GPUs have one, that they are there. The idea of having heterogeneous computing and not anything that is only on the CPU is a much more acceptable one. And that is good for FPGAs too. As for specifically for FPGAs, they're no longer just logic, and there's plenty of resources. Now, most of this crowd probably knows what I'm talking about, but this was a software summit, so I thought I didn't assume quite as much. So I'll have to continue doing that. We have now a large amount of memory on chip, which, for example, allows us to do bigger images or streaming larger amount of data on chip and process at full speed on chip. We have hardcore multipliers, plenty of them. If the market was to push for it, we could have floating point multipliers just as much. The answer from the company is that there is no market demand. We're not putting it there until you guys, namely Microsoft and the software community at large, take notice and demands for that. There is an interesting thing that FPGA, despite the low clock, keep on being able to process the highest rate of data transfers much farther ahead of any other ASIC after them. Another interesting element, perhaps the most interesting from a management point of view, is the market share that has shifted between pure networking and embedded at large. It used to be 90-10, now it's more like 40-60. And this is something that happens relatively recently. The most recent thing that's happened is as of roughly 2 years ago, the introduction of Vertex V6 and V7, is that the manufacturers are now paying attention to power a little bit and price issues. So you can buy a Vertex 6 for $10 in volume, which is at least a factor of 10 less than what it used to be. We're not at the pennies that ASICs might require for phones or other parts, but it certainly come down a lot. So when you put all of these things together, I think we can make the argument that this thing has changed in recent times. We're not, refrying the old story. So to prove that, here is something we presented recently at TechFest to the product guys at Microsoft. It's an application that, your shiny armor, everything is beautiful here, kind of application with very, very nice, this doesn't work, okay. Performance speedups, both in terms of rate of execution of the application and from a power perspective. And I'll come back to the power issue here. So what is it? This is spam filtering. Your large provider is structured pretty much like Microsoft.com, and that's where this thing is. This is really the Microsoft.com email domain, and Hotmail or Google, et cetera, are structured roughly in the same way. There's an initial whitelisting, blacklisting, meaning do we accept the connection from your machine, your known spammer? No, we don't. After that, we do spam detection. Well-known fact is 80% of the mail that goes around is spam. And so the brunt of the work in Microsoft domain is, in fact, to cut that out, to shunt the probably spam into slow path, and the other path take the fast path. There's more work that goes on, so this is an overly simplified picture. But it's clear and interesting computational load if we devote more than 600 machines just to this specific task of deciding if something is spam or not. So how is that done? And I'll get into more detail later, but basically it's just regular expressions, Perl regular expressions. All the providers agree with each other. This is the new spam mail. Here is the expression that capture it, dollar, Rolex, Kenya, whatever. And then you put them online and have this machine process it. Now, this isn't to say that we're running Perl on those 600 machines. This is a very optimized software version of it. So they take, in software, they take a regular expression, compile into small state machine, and a fairly high optimized machine loop process this thing as fast as you can. Still, each processor is a sequential machine that can only produce, at the end of the day, roughly 1 message per second. With the FPGA version, because the task is parallel and has other properties that we'll go into, we can get much higher rate. But perhaps more importantly is the wattage. Those are the measured power consumption at the socket. So this is AC watts, not DC watts. So whatever you want to quote your blade or PC, we measure 200 for the PC that we used, has to be compared to 10 watts for, by the way, the entire board, not just the chip. So memory is also accounted on that power feature. So that is not optimal, and this is probably not optimal either. But the ratio is very impressive. And if you talk data center, the power bill is the thing that dominates. Now, how does this happen? Basically, we take the basic regular expressions, match 0 or more, 1 or 0, or 1 or more, and we can map it directly into very trivial, simple circuits. One little trick we play here is the character matching, because this regular expression have a lot of URLs, very long ones typically, and so doing the character matching is the most biggest potential space-consuming thing. So what we did was to figure all the characters that are relevant, match them, transform that into yes/no single signal, so we don't have to run 8-bit buses throughout the chip. And that's basically the biggest space-consuming, space-saving idea. Here's how the system looks like physically. There is a software counterpart on the left. There is a standard support thing. By the way, there is a toolkit that we made available from our group called CIRC, Simple Interface for Reconfigurable Computing, which covered the problem of using these devices from Windows. There was no such thing, nothing like it before. And it's also vendor independent, so there is that benefit also. And I believe many people around, at least our company, and outside too, have found it beneficial. Somebody recently provided support for MATLAB for it. So that's what this part here is doing. The matching unit will decide if this is an I, if it is an L, if it is an E, etc. And then we run the wires throughout the chip, and according to the composition rule that I presented before. Now, what are the fundamental properties that makes it a shiny armor knight kind of thing? First of all, it's both massively and embarrassingly parallel. Nothing better than having 150,000 regular expressions. That's the amount of spam that we collected over the year, and it grows at the rate of 10,000 every 6 months. So what Microsoft.com in those 600 machine does is only keep the hot 50,000. They simply don't have the power to do all of them. We did all of them. So it's a very massively parallel problem. And it is embarrassing parallel. Every single regular expression is independent of the other one. It doesn't have state. So that was an interesting twist. So we can use partial reconfiguration to solve capacity issues, because the chip is finite and can fit roughly between 3,000 and 4,000 regular expressions. So what we do is to store the message in the chip, reconfigure the chip to run 3, 4, whatever happens to fit the next big stream every time. And still we can do all of this at a faster rate than the software version. Another interesting property is that it is a simple data access model. The messages stream in. There is no random data access, database, none of that. So very simple there. A couple of things for how we go about it. We follow the established success story of developing a domain-specific language. In this case, for regular expressions. Happens to be very nice and very something that the users are familiar with. We're lucky that it compiles nicely. But the thing that is also nice about it is that it compiles predictably. This is one of the very few hardware compilers that I know of. Maybe they are the only one, if you guys correct me on that one. They anticipate what is the size of the bit stream that it will generate. That is important because compilation times are very long. So in order to pack and split 150,000 regular expressions into the appropriate chunks would take an enormity if we had to do even binary search or any other way. This way we can just parse and see, anticipate how big does it fit, does it fit, does it fit? Yes, stop. And what am I saying? Yeah, and so with those large number of regular expressions eventually compiled in about 40 bit streams, and the prediction is within 7%. We try not to go to full capacity, otherwise compilation becomes very long. So we target the 80% capacity, and we are within 7%. We're always overestimated because we do not account for potential optimization the compiler can do, and the compiler does apply. So it's a conservative estimate, but still fairly close to the optimum. Other interesting properties of this is that there is a software fallback. What is it good for? Well, if a new spam comes around and you have to be online right now in the next 5 seconds, you can't afford even half an hour recompilation. Well, good point. So we can keep one of those 600 machines up running and run the emergency deal with this emergency now, and in half an hour we can recompile and get back into. And so that machine is not on the critical path anymore. It just has to run one expression or a few. From a more practical point of view, there are other properties that are interesting. In a data center, you always deal with this hot spares and failover issues. In FPGA, by its own nature, it gets reconfigured and reprogrammed as a matter of course, and we leverage this even further in this particular case. And so the time to bring online a new board, a new system is almost nothing. Now, what is bad about this thing? Much as it can scratch my head, not very much. Practical considerations is a non-standard device, is an improved technology, et cetera, yes, plenty of those. But from a technical point of view, this application seems to be all on the good side of things. And hopefully you guys can find some pitfalls or something and prove me wrong here.
It requires to have hardware people in your software business to maintain this.
Well, does it? Because the regular expressions, right? The operator, all he has to know is I typing a new regular expression somewhere and it happened, right?
Someone has to maintain this DSL.
Yes, so yes, that's the non-standard thing, but, and it's unproven, so what does it mean exactly? What are the failure characteristics? How long does a board last? How long should I provision for, as a new version comes around? Is it compatible, is it not compatible? There are plenty of practical questions, but from a technical point of view, it's got all the easy cases, basically. All right, so this is the so-called controversial part of the thing. And so the question is, well, how far can you push this thing? Can you use the one-size-fits-all paradigm? Can you claim that is actually valid? And I say, well, why don't we try to argue for that? I already mentioned the soft fab idea. And if we push it to the extreme, bigger and bigger and bigger and bigger, millions and millions and millions and millions of chips, how many of those can you possibly be? You can already fit an atom in it. So the biggest circuit you can build fits. So that's the existing proof that capacity is no longer an issue. The second bullet that I'm trying there is, what are the alternatives performance-wise? What can you expect from anything that you have seen in architecture realistically? What kind of performance multipliers? Factor of 4? Factor of what? And here we have 6,000 right now. The downside, of course, is that, you know, this does require part of the program for real, not for a joke, not with a couple of threads and the mutex, which is already trouble. Another thing is, well, if you were to push this technology, where are the low-hanging fruits? Where can you conceivably find successes? And I'd say power is one thing we can definitely sell, and that is definitely relevant in a data center and in a portable space. Obstacles, there's plenty, and my biggest one is usability. This technology will be around for 20 years and plus, and yet it's just as hard to use and program that it was 20 years ago. And all the specialized things and the tools, et cetera, haven't really changed. The paradigm is correct by construction, and yet is not matched by a viable ecosystem of tools that support that, except for MATLAB. MATLAB is the only shiny example of success story that you can reason within, with your DSP kind of architecture, and then it maps transparently, and it just works, and those that can use it are very happy customers. But there is nothing else for the general application domain. Even the language that we use, Verilog, has been stagnant pretty much for many, many, many years. Other languages made lots of progress in terms of type checking and usability and libraries and whatnot. No such thing here. Every time you build something, you start from scratch. The main concern has always been performance, not usability. But performance is nothing if you can give it to a user and actually do something with it. So usability is my #1 pet peeve. That is what we really absolutely have to go after and solve. But there are other problems. I mentioned that this is a parallel machine, and if we don't have the languages and the tools for programming it, we're in trouble. In the schools, we don't really teach. Certainly not in the CS side of the universe. We do not teach parallel programming at all. So it might be as bad as going back and scrap generations of programmers and start from scratch from there. Might be that bad. The power of this device is in spatial parallelism, and yet there isn't modularity. The tool is a whole program compilation tool all of the time. And that means not just that, debugging things is troublesome, composing things is trouble, but that there is no leveraging of, Unix came with libc. And that was a pile of functionality that was there and you could use and do something more complicated with it. We don't even have libc here. That's fairly depressing. Partial reconfiguration is the ability of reconfiguring the chip while it is running, so changing parts of the chip. And it's fairly promising in a number of directions for solving practical problems. For example, if you want to plug this into a bus, there is a portion that can continue working, or in our case, the network interface can still work while we are changing the system. But it's even harder to use than the regular tool flow. Xilinx has just, last year, I believe, officially started to support this feature, even though it's been in their chips for 15 years or so. Another big problem is portability. I mentioned GPUs, but there are a number of facts in the GPU domain that have made them successful. The fact, for example, that you have the shader programs that you can move from one device to the next, that is a degree of portability that is very important. We don't have that in this space. And lacking the modularity, there is no ecosystem of free software tools, academic, et cetera. It's mostly vendor-bound and price-bound. And I stop here. So this is the truth in advertisement clause. So that's nice, but if we really were serious and try to deploy this to the general population, I don't think we can avoid smashing our heads onto most of these problems. And I'll stop here. Question?
What's the answer to the rest of it? Do we have a new era of reconfigurable computing, or there's still the problems you describe are going to really prevent us from actually using on a wider scale these devices for compute?
Well, we are on the cusp. The potential is certainly there. But any one of these can be a killer. So I don't know what your answer is. My problem is usability. If we want to, make a general purpose to the population, we're not in a condition to do that at this time. Not much of a pipeline, meaning the pipeline is within the regular expression, as you can see, because you have to compose this. So they're all independent. So that's good also for a clocking point of view. Latency is, 1 character per cycle, and we target gigabit Ethernet speed, so 125 megahertz is good enough. We ported it to a Pico card using a PCIe bus, and that was not, it worked fine. So timing is not as much of an issue. We did have to do register, automatic insert registers if the regular expression becomes too complicated, so the tool will do that. So is that the question?
I just wondered if you could fold things so that you can do more than one expression on the same piece of hardware, given that you could clock things a bit faster.
Every configuration packs between 3,000 and 4,000 regular expressions on the chip. And then by reconfiguring, we do the next 3,000 or 4,000, then the next 3,000 or 4,000. Okay, so it's an interesting use of PI for capacity purposes, not for functional purposes. So we don't do something different in the next step. We do exactly the same thing, but it's a different set of regulars. So it's not a processor at all. No. Okay, so. Okay. Thank you.
I'd like to invite Quipu from Dell to give us his answers to these questions.
Yeah.
Before you get wired up with the mic.
Okay. Yeah, okay. All right, so I'm Koen Bertels from Delft University Technology, and I'll talk about the research that we do in Delft, and was done largely in the context of a EU project called HARTES, with Wayne Luke also as one of the main partners. So I'll briefly introduce, but Alessandro's already done that, so I can be short on that, why FPGAs may have a role. And it's a conditional statement that I have, and I'll explain also along the same lines as Alessandro why it may be a may. And what are the specific challenges? Then what are the answers that we try to provide? What do we offer this field? And a big part in the answer is the word molen, which is a Dutch word for mill, a windmill. And it simply means that we try to make FPGAs look like regular computers and then improve thereby their programmability. That's in a nutshell what we want. So I'll also present the toolchain that we have built on top of this particular abstraction layer, which we now call BlueB, and I'll explain why, because it's basically a spin-off from this EU project. So yeah, Alessandro has already said so that there are some challenges in the semiconductor field, and that make companies like Intel look for other kinds of solutions in order to still get performance improvement. And in the computer architecture field, one clear direction is to go for customization of hardware. So rather than having homogeneous processing units, you want to have heterogeneity so that you can have computing cores that offer a more optimized circuitry for particular tasks. So I think this is this is maybe the biggest potential for FPGAs, because FPGAs are exactly good for doing that, offer dedicated hardware for tasks, and you don't really know in advance for which one. They can also change over time, even in one execution span of an application. The requirements may change due to some context changes like reduced bandwidth or low power, and you want to be switching to different kinds of computing modes then. So it's clear that the heterogeneity and the multi-core is there. Now, in the general problem of these kinds of platforms is to be able to use those resources in an efficient way, because it's not, we all know that parallel programming is not a simple thing to do. And then if you introduce more heterogeneity, then you even further complicate the problem. Now, how do FPGAs fit into this? But in this big picture, well, this is I think a very, very high level, but an easy to understand a picture that others have shown also. If you want to evaluate different technologies in terms of flexibility and performance, then FPGA score relatively well on those two axes, because they do provide high performance, in a power efficient way in most of the times also, and they have the flexibility. So they have the performance of ASICs and the flexibility of pure software programmable processing units.
Do you not have GPUs somewhere on that chart?
Yeah, well, GPUs are of course high on performance. Yeah, I don't think they're so flexible. They have the same problems, I think, as FPGA. So I would maybe put them in performance depending on the kinds of applications. Maybe even a bit higher than FPGAs. But that really depends. If you do a lot of vector processing, GPUs are good. But FPGAs, they're good at other kinds of things. Yeah. So yeah, I should add GPUs there too for the next. Now, our view is how do we use FPGAs? And it's more like what Alessandro was saying. It's for accelerating tasks. Now, we have a very specific starting point, namely that we think that if this technology would be picked up by the embedded systems industry, for instance, because this is what the companies like Xilinx and Altera are going for right now, is that they have this huge code base, and you cannot simply tell the industry like, okay, just redesign the entire code base you have and bring it to FPGA. So that's of course absolutely not an option. The only thing that companies are interested in is in using maybe some heterogeneous computing components to accelerate. So you have your application and you figure out that certain tasks are well suited for maybe a floating point DSP or for some FPGA, so you can have some kind of performance improvement. If you can also extract some kind of parallelism, high-level parallelism, because of course FPGAs, they're very low-level parallelism, but here we're reasoning in terms of programming and software development concepts, so more high-level, then you should also be able to exploit that. So this is our goal. How can we support this particular objective? And in the project that we're currently involved in, where the embedded systems industry players are there, like Thales, ABB, Siemens, they all say, well, yeah, we might be interested in FPGAs, but they're very difficult to program. And so if you don't address that issue, exactly as Alessandro says, forget about it. We're not going to make the investment, because hardware design is completely different from software design. We have computer science master programs, and we have computer engineering programs. We don't have anything that bridge those two things. Yeah. And as I said, this is one of the big challenges also for them. Now, industry is already moving. There are already an increasing number of platforms that actually offer the hardware in which traditional processors are combined with FPGAs, like the Convey machine, which has Intel processors with FPGA, the Xilinx 6 or 7, I think. Xilinx is announcing now this Zinc. There is also an Atom Altera being announced, or a MIPS Altera, etc. So there are these platforms are popping up, and so this is exactly the kinds of machines that we envisioned for our research. So as I said, yeah, they're difficult to program, we know that. They still have, take it or leave it, they have limited resources, yeah? Because we don't have all these mechanisms yet of virtual memory and these kind of things, yeah? So this is a severe limitation. Now, there is this emerging technology like hardware compilers. There are a number of them already on the market, but they have still quite a number of limitations. And ideally, of course, and I'm looking at C, embedded systems are usually still programmed in C. Yeah? So usually they take that as an input, and then they try to generate some kind of VHDL or other kind of hardware language. And they're still not as good as software compilers, yeah? Because there are many limitations in the C that are being imposed, and in most cases they even force you to write C almost and then in a hardware way, so not in the traditional sequential way. So there's this gap that still exists between the hardware and the software design. So this is what we set out to do. Now, how? Yeah, we try to come up with a solution that's as simple as possible to make the step into the FPGA world or the use of this technology as simple as possible. Now, as I said earlier, there's this Hartes project, and we're starting a company now. Imperial College and Delft are taking the initiative to try to bring this to the market, to bring it to the community. Now, what is the approach? Well, how do we make it as simple as possible by adding pragmas to your C code? Now, pragmas are a very powerful and simple technique that any C programmer understands. So what we have defined are a series of pragmas that will instruct, yeah, the tool chain, and therefore and later on the runtime support of what exactly needs to be done. So, for instance, this pragma indicates that this function should be mapped on a piece of hardware, which is, yeah, you can have an XML file that actually defines that this is a DSP, a floating point DSP. So this is important information because further down in the tool chain, you need to initiate the specific DSP compiler, yeah. And so then you will get, for this particular piece of function, you get the appropriate binaries. This is another pragma that says, okay, now we map it onto an FPGA, and it's this function, the function B. And that also has importance because now you need to invoke a VHDL compiler. Yeah? And so this is the approach. It's as simple as that. Yeah? And of course, all of these decisions about what to map can be either done. Yeah, we have developed some algorithms that help you in determining what parts are most suited for what particular hardware component.
What do numbers 1 and 2 mean at the end of the pragma?
Because you may have, this is just an identifier. Yeah, this is an identifier. That's all. Because you can have multiple computing units also at some point. Yeah, and so what you want to do is to take into account as early as possible your available resources. So this DSP, for instance, can only be loaded at the start, so no runtime changing of your code. But if we can have up to, yeah, I'll show you later, we can have up to 5 custom computing units. Yeah, and so you want to keep track of how many you've been doing. Now, bottom line, is it really that simple? The answer is mitigated, yes and no. Yeah. Yes, we do say that the pragmas are the only thing you need to do, but of course behind the scenes a lot of things still need to be happen, and hopefully that's the goal, to do that as automatic as possible. Again, with the idea that a normal or a pure software developer should be able to do this, yeah, and target DSPs, FPGAs, GPUs. We don't look at GPUs because Wayne does, and he doesn't even need to know about that. Yeah, that's the idea. So how do we do this? Well, by making an FPGA look like this regular computer, and we do that by defining a Mullen architecture. Now this is the picture. Nothing complicated if you look at it. Yeah, we recognize, yeah, the general purpose processor. We don't care which one that is. Yeah, we can have FPGA fabric here. We can have DSP here. Yeah, and then we can have custom computing units as long as we have resources available. Now, all of the, in main memory, traditionally we have data memory and we have the instruction memory. So the instructions reside in memory. You fetch them, and there is the arbiter, because the pragmas, of course, in the end, they initiate a number of things, because that means you need to configure a particular custom computing unit, or you need to load some code here. And then at some point in time, when the execution needs to start, you need to actually initiate it. So we have instructions that are being introduced by the compiler to actually configure, which is a set instruction, or execute, which is the execute instruction. And those instructions are specific for those devices. So the arbiter here is retrieving the instruction and says, oh, what do I read? Is this a general purpose processor, just instruction? Let it go. Otherwise, redirect it here, and this thing actually controls the configuration and the execution of those CCUs. These things have their own, the H is there wrong, they have their own scratchpads memory, but in principle they can also access the main memory. There are some register files for the GPP that we all know, and there's dedicated exchange registers that allow the general purpose processor to exchange information like parameter passing, an address, a pointer to memory. This is done through these exchange registers. So this is the Molen machine, and this is applicable to a wide range of real devices. So in this Hartes project, we had an ARM here, we had a Vertex 4, and we had the Diopsys from Atmel as a DSP, on a single PCB. So that was the platform. So the Molen architecture, in a nutshell, is a one-time extension of the instruction set architecture to implement arbitrary functionality by set and execute. And you don't really care what the set and execute in the end do. The only thing, these are the only instructions you need. A couple of more, and I'll show them immediately. So what we did, for instance, now is to map this abstraction layer, this Molen machine, onto the Vertex 5, which has a PowerPC, and then we have some CCUs here. Picture of the chip here is where you recognize the 5 custom computing units. And so the Molen infrastructure is on top of this. So that means that we can now easily find or map up to 5 simultaneous custom computing units on the platform and execute them in parallel if necessary. And we want to have now, of course, the tools to support that. So this is what I will now talk is what does this tool chain look like? First, some experiments that we did in the Hartes, just to show that this actually works. We have, for instance, we did a noise filter. So in 2 minutes, we could actually compile, excluding the synthesis. That's always the real bottleneck, and that's why you said we still need a soft processor in order to do the real urgent things. It's important that here we mention application speedup, because and it's not as impressive, of course, as your 1 second to 6,000. Because we're limited here by the inherent sequential nature of the application. And there is always a huge bottleneck, and that involves the data communication, because the Molen machine assumes that there are all communication channels, but in practice you're limited by the bandwidth that all of the hardware gives you. So we have here a 3x application-wide speedup, and that's I think still impressive. By doing this in 2 minutes, you can speed up from a simple ARM-based execution to the ARM-based FPGA DSP combination. Wave-field synthesis, that's for 3D audio, where you can replicate the spatio-temporal characteristics of sound. We can have up to a 1.8, 3.05 application-wide speedup. We also did an application, a kernel Rijndael encryption, and there we achieved a 20x kernel speedup. Now, if you compare that to one of our PhD students, he did a manual design, highly optimized, with a 700x speedup. Now, if you embed that in an application, the difference in speed up application-wise was only 2%. Why? Because it's only, this is Amdahl's law also, the impact that it has. So this is the good enough message that Alessandro also gave in the beginning. If it's good enough, it's good enough. Why squeeze out 700x if you don't really, if it never really is being used to the full extent? Yeah. So these are the numbers that that we do. Now, what is the tool chain? So again, this is the outcome of the Hertes project, but it's called now BlueB. So we have a C code. Yeah, that's always our starting point. And what you want, of course, is as early as possible you start understanding what the implications are of certain choices. Again, same problem, because the lower you get here in those tools, especially this part, because the synthesis tools are proprietary. Yeah, we don't show them here. Yeah, but this becomes the huge bottleneck. So whatever decision you make here, translates in a lot of time-consuming things down there. So you want to exclude things that are basically impossible. Why? Because you don't have the FPGA resources, for instance, or you don't have the bandwidth, because you may implement the entire kernel on the FPGA, but still you cannot get the data in fast enough. So those are typical problems that you need to look at. So what we try is to come up with as early as possible with some, and I'll give you some examples. So you determine here, the red thing says, okay, this will go to the FPGA part, and this will stay on the general purpose processor. And parallelization, we don't do that. Yeah, there are parallelizing compilers available. The entire approach can handle OpenMP. So if OpenMP annotations are there, we can schedule all of those tasks in parallel. That we can do. Yeah, we don't do that. So but we can take any parallelization compiler, and it will produce, of course, annotated C code, and then there will be task transformations, and I think Wayne will highlight some of the things that are in there, and some extensions that they envision now. And then again, so we determine which parts should go where, and then through those pragma annotations here, this will initiate the respective backend tools that you need. So here we will have some VHDL that's being generated, and here we have the general purpose or the C compiler here in our case that will introduce all of the necessary stitch codes, and I will show that in the next slide a little bit in the larger picture to get an idea of what now actually is being done. So if here we have the original C with the pragma says, okay, this thing goes to the hardware, then this is normal intermediate code. And this is now what our compiling will generate. Then you will recognize here the instruction set extensions that I explained earlier. We have the set to configure, we have the execute to start the application, the execution, and they're moved to exchange registers and moved from exchange registers where a result is being placed in that specific exchange register. Of course, this is a simple example, and normally what you would not do is put the set here so close to the execute, because the configuration may take some milliseconds, and then you have to stall this thing. So we have, of course, algorithms that will move up. Yeah, we have data flow equations that will move up all of the configurations as far, but not as far enough in order to hide the latency of this particular configuration. The entire approach supports partial reconfigurability, again, to the extent that the platform actually efficiently supports it, which is not really the case. So, so this is what is being done behind the scenes. And as from a programmer point of view, the only thing you need to do are to put these pragmas. So the dwarf compiler, for instance, so you give it a piece of code, which is maybe only this part. It will generate some kind of, it will generate a data flow graph of that particular part, a hierarchical control data flow graph, and then do some transformations so that you end up with a hardware circuit yeah, and then you want to embed it, of course, in the larger part, and you need a finite state machine, which is also automatically generated so that this particular circuitry is being controlled. Yeah. So, yeah, is it now really that simple? Yeah, we would like it to be that simple, and there are still some constraints, especially the resources and the communication. So when you put everything on the FPGA, you of course kind of avoid some of those problems. But if you have a general purpose processor, shared memory, and then those FPGA devices, then you really need to move data around and get it there where it needs to be processed. And many of the approaches that look at FPGA mapping, they look at CPU intensive parts of, yeah, they do the simple gprof thing. And yeah, that's true. That's one way to look at it, but that's not necessarily where the bottleneck resides. So you have to really explicitly take data intensive communication parts into account, and therefore do the same thing as with caches, exploit the data locality. That's what you need to do. I don't have time to really go into detail, but this is a study that or a thing that we're currently doing. We look at an algorithm that does this edge detection, and we try to understand early in the design stage, yeah, what the communication patterns are, because CPU intensive things is one thing, but as I said, it's where the data is. That's the real challenge. So we're profiling a number of things. I'm only putting here. Yeah, we really compute the bandwidth that is being used by functions. We look at source level, yeah, because not at assembly level, yeah, but we look at source level. What variable is writing to what memory address, and what other, yeah, variable is consuming, or instruction is consuming a value being stored. And this is the quad tool that looks at memory bandwidth, also looks at unique memory accesses. Because this is an indication, if you want to move things into the FPGA, you need to know how much you need to reserve. What's the local buffer or the local, yeah, the BRAM that you're going to be consuming. You also want to be looking at dependencies between functions, because if two functions are intensively communicating, then you might be wanting to simply merge them and make one big function out of it, and maybe that function can go to the FPGA, and you already eliminate a lot of communication, writing back and forth to memory, for instance. We have another tool, the Quipu tool, which allows, when you have, for instance, the quad will say, okay, maybe we can merge these two functions, yeah? Then Quipu will actually tell you whether you have enough resources for this. So it's a quantitative model based on statistical analysis that will predict at what piece of C code, yeah, can map into a particular hardware resource. So those two things combined, yeah, we're now doing this exercise. This is ongoing. So where you profile and you see, for instance, that there is this function canny, which in total consumes up to 140 milliseconds, but actually it itself is not doing anything. Yeah, it's basically those two functions that are doing most of the computation times. So what you want is to understand how all of these functions in this list, how they relate. Yeah, and then you try to understand at the high level how the application looks like, yeah, and then you see the flow of the data through the application up to the end where you write back the image with the edge detections in it, and you try to understand here what the number of bytes are that are being written or read between those two functions, and they give you an indication of what should be maybe merged. Because one of the things we observed is that when you do this kind of analysis, you end up with relatively small functions in the code. And then, of course, you partition it so much, and then the overhead of using the FPGA becomes too high. So this is one way of making all these kernels bigger. And, of course, remember the layout of the Bolo machine. We have 5 equal size slots, so you need to be you need to understand when you want to merge whether you have enough resources. I'll skip this slide. Yeah, this is again the pragma. Yeah, so we are now merging a function and mapping it on the hardware, and of course you have to do something with the memory allocation. But I don't have enough time to. Yeah, so here we say, okay, now this is what the Quipu will say. Yeah, it will estimate how many slices it's going to take for you to actually map this function onto hardware. Yeah. And there are about 25,000 slices on the Vertex 5. So there are some limitations. So you already know that this one is going to be difficult. Yeah? And you can investigate, like, oh, why is this so big? Well, it's big because there's a local array there. And if that is translated into flip-flops, yeah, then you already lose almost the entire available space. So there are ways to then start merging. Yeah, you create new piece of C code, and then you can go back into the tool chain that I showed earlier, and you can keep on merging. Yeah, to make it as big as long as the payoff is positive. Yeah, and so there are other things you need to look at then. Here, for instance, there is also a large local memory that's being used. So we are now looking at techniques in order to really quantify that, to understand how the memory is used throughout the application lifespan, and then to determine also the optimal size of the local BRAM. So you can continue like this, finding good mappings. It's an iterative process. It's never a single shot. And so in summary, do FPGAs come to age? Yeah, they're not necessarily low power, but they're energy efficient. Yeah, and I think FPGAs, I said in the beginning, are definitely one technology to introduce is heterogeneity, and we see that already happening in real-world platforms, yeah, like the ones that I mentioned. Unfortunately, and this is still the big issue, that hardware design is completely different from software design. And so bridging the gap is one of the challenges. And for some strange reason that I never really understood, and now they seem to start to regret it, FPGA manufacturers like Xilinx and Altera, they basically, well, Altera may be a bit better than Xilinx, but Xilinx never really invested in any higher level programming tool like the one that I tried to explain here this morning. So, and I think this will be the showstopper for FPGA technology. We already see that in the embedded, these were numbers I saw recently, that the adoption of FPGAs in the embedded systems industry is shrinking in the last couple of years. And it's basically because of the lack of programmability. Yeah, and so we try to bring this one step forward by this spin-off that I mentioned earlier, and we try to have a release of the entire tool chain, as I said, towards the end of the year. So thank you very much for your attention.
Thank you very much. Any questions? So I'm always perplexed by people in stuff with C. Yeah, but surely there are better choices for the task at hand, or even looking at things like BlueSpec. There are some examples of more civilized ways of doing hardware design that's not more of a software.
Yes, you're right. But again, as I mentioned, we focused from the start to on embedded systems, and embedded systems are still 80% written in C for legacy reasons. Yeah, but this is the way that the industry works, and I think this is one of the challenges that we try to address. Code base, yeah, legacy code base, because yeah, the largest code base is maybe not C#, but it's still COBOL, yeah, in the world. So you can simply not say, well, we don't care. We just move ahead. Backward compatibility is a big problem. Yeah, I mean, Intel had the same problems too. So this is just a fact of industry, not the wish maybe. Yeah, and that's why. So you're right, yes, but we cannot do much about it. This is reality. Yes, sorry, she had a. Yeah, but I think
I'm not saying that it should be done automatically.
Yeah.
I was just curious.
Yeah, so we have an automatic approach and a manual approach. So in some cases, the developer really understands his own application and says, okay, this is what I want to accelerate. So I put my pragma here. Yeah, I think Wayne will give some insight in how you can automate this. Yeah.
Okay.
So I didn't have time to go into that, but I think Wayne will explain that.
I'm glad you guys are starting to talk about word domination and FPGA. I know you're talking to the converted, but I wish they were more compiled.
Exactly, we're yeah.
Over here, I mean, where are they?
Yeah, that's true. Yes, please.
So, Xbox are trying to compete against FPGAs. You know, they have these little parallel processing cores, and they have a language XC, which is basically C, but with some parallel constructs and some message passing, so that you can, you know, receive something on a channel and put on another, and then
Yeah.
the channels can actually correspond to physical pins, so you can do FPGA-like things. I'm just wondering, I mean, had you thought about using a sort of superset subset of C in order to get these sort of parallel constructs? So at least you'd be starting from more of a parallel base.
Yeah. Maybe I'm too pragmatic in what I do for research, yeah, but I think there are more than enough initiatives on parallel languages, yeah, and approaches around. And I don't think that anybody is waiting for me to add something, yeah. So even using existing approaches, unless there is something really dominant popping up, yeah, then I don't want to look at it, because everything has its pros and cons. And what I think is what I really want to do is bring a solution to industry that they want to adopt. And if there is too much of a paradigm shift, and if you cannot really connect to the way that they're programming right now, you can forget about it. Even this is already pretty far-fetched for many of the people. Yeah, and I said I'm with ABB, Siemens, yeah, Selex, Finmeccanica. And they all say, yeah, we would like it, but it has to really be as close to what we're used. And still at the same time, have all of the low-level controls they want. So if you then come up with something, wow, this is a very powerful parallel, and I'm sure, yeah, I'm not an expert in these things, and I'm sure there are very many good approaches. But again, they are orthogonal to the way that people are used to, and then you can forget about it. It will stay a very marginal technology.
I think that's one thing that's interesting about XC is it adds a bit to C, and the bottom line is Xbox is shipping products, and you know they're getting software engineers to easily adopt their tools. I believe. So,
Yeah, but I will look at it. I'll ask for the reference after this session. Yeah.
Xbox, yeah.
Okay, yeah. Then I'll look it up and see if that's useful for us. And if it is, if we can hide it, but then we should be able to hide it. Yeah. And not expose it to the developer, because I think this is one of the big problems. People don't want that. They cannot do that. They don't want to have the investment. And yeah, you should not forget that this is what the Siemens people told me. They still work in VI. Yeah, they use VI for programming, so they don't even go for any modern IDE. Yeah, a NetBeans or an Eclipse. Forget it. VI. Yeah, and that's fine. But you see then what big step they have to make in order to reach the more sophisticated approaches that you're talking about. Yeah, so that's the limitation, I think.
I'm very skeptical about your comments about hiding it. Right? I think you can't get things for free. You can't automatically parallelize programs in general, which is the same structure.
Exactly. Yeah.
Circuits. And often when we want something for nothing, we usually get nothing for something. Well, thank you very much, Chris.
Yeah. Okay. Thank you.
Finally, we've got Wayne Luke, who's a professor at Quipu College, and he's for many years worked in various projects to raise the level of abstraction for programming FPGA circuits.
Thank you very much, Satnam. It's a great pleasure to be here today. So I think I will give a slightly idealistic inclination to the discussion, although as usual about these things, that one would usually draw to the same conclusion wherever one's approach might be. Okay, so just an overview. So what are the motivations, promises, and challenges? I think one way of getting something towards coming of age would be make sure that it will be efficient, and also the design method would be productive. Okay, so and I'll provide some current research about how we one way of achieving this, and then discuss some results and further research directions. Okay, so as far as efficiency is concerned, one question is that, well, can we find ways of transforming and optimizing designs which would allow us to control the improvement to get the best trade-off in area, speed, power consumption, energy consumption, and so on? And can there be some assurance of optimality? Okay. And then as far as productivity is concerned, are there ways to allow us to search or to find these optimal designs, if, assuming that they exist? And perhaps if we could find ways of reusing the designs and transformations, that would be one way of achieving the goal. And of course, those who have attended yesterday would appreciate there is this discussion about verifiability, which currently we are not spending very much effort on, but we appreciate this is an important discussion, and I'll, when I talk about future work, I'll talk about the direction that we are achieving. So this is more about the background, and I will very quickly just describe that one way of seeing reconfigurable computing as being a combination of the technology that could be reconfigured. So that includes FPGAs, but not necessarily exclusively confined to FPGAs. And indeed, a lot of what I'm going to describe could also be applicable to GPUs, as Kun just mentioned. But just as important, not just the target technology, but also the way of thinking and developing these designs. So that I think the main concern or the main promise is how to exploit the flexibility or the reconfigurability of this technology so that we could customize the parallelism or customize the amount of data access, or indeed customize the data representation in order to achieve the best trade-off for specific applications and for different domains. Okay, so well, just to provide a very quick summary of various promises. So that's some work that we did a while ago to demonstrate that for encryption applications, not quite as much as 8,000, 6,000, but we did have 3 order of magnitude with the best software implementation at that time. And someone else looked at biological designs for reconstructing genomes, and they also conclude going from 400 to 1,000 times faster than software. And my colleague Oscar Mensa, he has a spin-off company working with JP Morgan, and they find that one could achieve 30 times faster per cubic foot and per watt. So they're thinking about implementing these things in data centers and so on. And JP Morgan does have quite a large amount of systems in data centers. So I think these are some of the perhaps evidence that this is a promising approach, and it's not entirely idealistic. Now, what are the challenges? Well, how can we achieve optimality? Okay, or are there ways to even allow us to specify what would be optimal? The other question is, well, how can we verify that we actually achieve the functionality and also the performance goals, and also how can we make it easier. So I think Kun already summarized that a lot of existing hardware compilers are not always optimal, and probably in many cases they may not even be correct. But on the other hand, there aren't any established models to check behavior and performance and so on. So I think these are some of the directions that would be promising. Okay, so if I just quickly talk about a particular experiment that we've been looking at. So the idea is look at specific design templates, or I guess those of you who read the well-known paper from Berkeley, that they have 13 WOFs and so on. So this, when I say talk about templates, that could be seen as one of those. So we could verify the parameters, the architectures, the representations in order to develop different implementations. And then the idea is for the development, one could start with something relatively obvious or an existing design which is well behaved, and then try to find ways of deriving better implementations because of a newer device or newer requirements and so on. So in this particular approach, we identified there are two different kinds of transformations. So the first one is called pattern-directed, and these are fairly obvious. So it simply means that transformations that the designer will need to explicitly provide the source pattern, the transform pattern, and also the conditions to which the transformation could be valid. So in a very simple example, it says if these conditions are correct, then one could transform this expression to this expression. Okay, so you could imagine this is a kind of loop merging, and I'm sure Satnam would be very familiar with this transformation, because this is some work that he and I worked on many years ago on a language called Ruby, but this is not the current Ruby scripting language that many of you might have used. Now, so this is the pattern-directed transformation. The other transformation specified by the constraints and objective functions as people in mathematical optimization have been used. Okay, so the idea is to try to model systems following the sort of models and constraints that many people in mathematical optimization have already been looked at. And in many cases, it was found that as long as those constraints can be expressed in a certain form, then efficient solution procedures could exist. So in particular, there is a method called geometric programming that we've looked at. And so as long as the constraints are expressed in a certain format, then there are automatic search procedures which could highlight solutions to those constraints and find designs in polynomial time. Okay, so what's been done is that we've looked at models that could capture two different kinds of optimization. The first one is data reuse, and that simply means that identifying applications in which access to off-chip memory could be systematically copied to the on-chip memory, so that one could reduce the amount of off-chip data access as much as possible. I think that the optimality, the ideas of doing that. I think that's been highlighted in Simon Moore's talk. Those of you who attended that talk would not need me to explain any further. But the question is, for particular application, how can we do it in a systematic and optimal way? And then the other optimization, which is also quite well known, is how can we parallelize and pipeline designs. So for example, if one could think of this as a single processor which being used to implement a loop, the other possibility is to develop a pipeline implementation so that the data could flow through elements of the processes one after the other. Okay, so that would have the advantage of increasing throughput, and quite importantly, it also would tend to reduce dynamic power consumption because it will tend to reduce glitches in the implementation. Okay, so the design template that we've looked at is a relatively simple one at this stage. So that is the well-known map reduce. So that says there is a map stage where data go through identical processing, and then the result of that would then be fed to a reduce stage, which typically involve an associate operator that combines the result of the from the map together. Okay, so I'll just show in the next few slides, give you a feel for what the model might look like, but not going into too much detail. So I'll start with this utility directed transformations, and the word utility simply means that we'll try to optimize a utility function in which, in this particular case, we try to minimize a model of the power consumption of this application. Okay, so the details doesn't really matter, but we try to map a n-level nested loop into a design like that with various on-chip memory elements, and the challenge is to find the appropriate mapping between the references to the variables, to array references in the application program, and map it onto the available on-chip memory, and also related to the processes, and so on. So one could go through the model, look at the off-chip power consumption, the on-chip power consumption, and so there are various ways of expressing the constraint, and some of you who know transformations will know that this constraint is expressed in this form called a polynomial, and the idea is once it's expressed in this format, then there is an efficient design procedure allowing us to search for a global optimal within this model in polynomial time. So that is the motivation of doing that. And when one could do something similar to find expressions of constraints in this particular format for speed and also for the resources. And there could be different kinds of resources for computation as well as for memory. So once it's been expressed in this format, there are still questions that that particular form may or may not be the most obvious format. So we find that in many cases it's useful to have a initial transformation, and that is transformed by the pattern-directed transformation, which involves the user specifying inlining certain operations or changing pointers into arrays and so on. Okay, so once it converted into a certain format, we check that the utility transformation could be applied. That is the applicability analysis. And once it's done that, then we could actually apply the transformation and then look at how efficient the result would be. Okay. So the remaining bit of the talk, I'll explain briefly about a transformation engine that we've prototyped. So we aim to supply or to support a library of transformations involving both this pattern-directed as well as the utility-directed transformations. Okay, and in particular, find ways to make sure that the results of one transformation could then be fed to the next stage, so that one could continuously transform things until either it's proven that this is the best one could achieve, or that might not be a solution. One needs to change the requirements in order to, for realistic implementation to be found. Okay, so some of the requirements will need to combine different optimizations and also to provide different parameterizable transformations in the system. And then, obviously, a lot of these transformations could also, I mean, there are multiple ways of expressing it. So it is still a matter of getting experience to find out the best way of encoding a series of transformations. So the implementation, which I'll explain a little bit more, is using both a scripting language and also another language called Rose. Okay, so a little bit more detail. So we have building a library which allow both application independent as well as application specific transformations. So for example, for applications that involve video and imaging, then obviously there would be transformations related to arrays of pixels and so on. And then some of those would also be applicable to imaging applications and not necessarily to other applications. But there are other more general transformations like merging loops and so on, which are more applicable to different applications. So there would be a playback mode so that one could actually look at the result of applying different transformations to check that it is really doing the right things and achieving the right results. And then there are simple composition and also more complex composition like checking the preconditions of transformations. One could apply multiple transformations at the same time and see which one gets the best results. But then getting the best result might only be a local optimal, so one might need to look at larger sequences in order to see which one will get to the best implementation. The implementation itself right now, there is the transformation engine which applies specific transformations. The prototype that we have, we use Python to script the combination of different transformations together. The individual transformations are implemented using a system called Rose, and that is probably the most robust system that we found. We used other systems before, but find that we seem to spend more time debugging the framework rather than building our own transformations. So this is just a very quick view of what it looks like. And so right now, that is the starting point. These are some of the loop-based transformations for the pattern-directed. There, over here, I think that this one is a utility-directed transformation involving the geometric programming and so on, which is the involving the optimality search, as I outlined before. Okay, so I think one could definitely improve the layout of this description and so on, but that just gives you a feel for what it looks like. So very quickly show you some results. So we look at various application, matrix multiplication, edge detection, and simulation for in a finance application. And we look at sequences of transformations that we have found to be useful and compare them and so on. So these are some of the transformation that was outlined. So merging the loops, decomposing complex expressions, and improving the instruction level parallelism. And the platform we have, in this case, there is a Xilinx Vertex 4, but we are now changing it into Vertex 5 and Vertex 6. We just got those not so long ago. And then one could set constraints about what are the speed and the size and so on. And then one could also put a limit on how long the optimization procedure could take. So if you want to go for a cup of coffee, then you could set it to a longer time so that when you come back, hopefully it might give you the result, or it might say you can't find the amount, any result in the given amount of time. Okay, so there are these are some of the results showing the trade-off between execution time as well as the amount of resources for different applications. So for example, if one apply one transformation and then the other one, then one could improve the speed. But if you apply the change the sequence of optimization, then one could improve the amount of resources, for example. And then one could also look at the trade-off between execution time and power and energy consumption. And as you can imagine, that if we want to have a short execution time, then the energy, the power tend to be quite high. But if one could relax it and make it slower, then one could reduce the power consumption. But since we know that energy depends on both power and speed, it turns out that at least for certain application, for this application, one could actually find a minimum of energy. So if we want to minimize energy, then we could actually find a sweet spot in this particular application. And then we could, again, compare different ways of transforming designs for these financial applications and so on. Okay, so some recent directions. So what we're doing is to make it part of our transformation engine to be incorporated into the larger system that Kun mentioned earlier. And I think that is the Toolchain that Kun and I used to work in part of the European project. We're also experimenting with ways of capturing the transformation using the ACL2 theorem prover, so that one could try to verify the transformation themselves, because obviously it would not be very good to improve performance but get the wrong result. So we experiment with a combination of symbolic simulation and also equivalence checking and so on. So this work is still ongoing.
We can consider wrapping up soon.
Okay, yeah, we are very soon. And also we also look at changing the representation so that one could, for example, reduce the accuracy. The idea is if we have 1% less accuracy, but it might lead to 60% improvement in less area and possibly reduce power consumption and so on. And then there are various theoretical and practical issues that one could focus on. So, and I'm not going into details. So I think the conclusion is that, well, it is coming of age rather than it has already come of age. So I think current work by ourselves and others have demonstrated the a lot of promise, but I think in order to make it realistic, I think Sandro mentioned how to make it more usable and so on. And we hope that what I described would also make a small contribution in that direction. Thank you very much.
Thank you very much.
Okay, people want a cup of tea or coffee? Simon.
Are you doing any work on handling floating point numbers and optimizing floating points?
Yes, we do actually. Yes. And I think it's quite tricky to define correctness if you want to look at for example, the IEEE floating point standard. I think in the past there are people who try to formalize the floating point. But yeah, no, we are definitely, I mean, for example, the work on data representation look at comparing standard floating point versus customized floating point versus different representations. So obviously there is the fixed point. There are logarithmic representation. There are redundant representation. So it depends on, for example, if the application has a lot of multiply and divide, it might mean that logarithmic representation would be very good. If the application mainly has add, subtract, and so on, well, it might be the case that we could convert that into a fixed point, for instance. And indeed, one could, again, we've been looking at whether it's still efficient to obtain a mixed representation. Okay, so again, FPGA allow us to do that. Whereas on a GPU, well, you got fixed amount of resources in FPGAs. One could actually possibly looking using the kind of optimization that I described to see whether a single or a mixed a combination of different data representation might provide the most efficient combination of speed, area, as well as power and energy consumption.
I think we should probably just get our coffee. Thanks to all three
Okay.
speakers this morning.